Good morning, and thank you for joining me to listen to the first lecture that we have regarding our chapter 6, where we are now focusing on semiconductors. So maybe I will start first by noting this trend that we have in our lecture, that previously, especially in chapter 5, we were focusing on the type of materials known as conductors, in other words, metals. And now in chapter 6, we will be focusing on semiconductors, and we want to understand their electronic properties. And then finally in the chapter 7, we will be focusing on dielectrics. So that we are trying to cover these different main categories of materials during our introductory course. And now we will be unraveling the basic 101 on semiconductors. So this is the kind of overall logic we also have in our course curriculum, so that we want to also elucidate to you the different types of materials and the main properties that are associated with them. And since with metals and semiconductors, it's essentially their electronic properties that are most often of interest when we are thinking of applications, then we are really focusing on their electronic properties. And then in dielectric materials, we will be slightly shifting our focus to something else, since in terms of applications, dielectrics also have lots of other applications that I could at least think of. So this is what we will be covering in essence during the next few lectures that we have. And here we will be starting our journey on chapter 6. So first, in this very lecture that I will be now starting soon, we will be introducing the main terminology that we have on semiconductors. And we will start by showing you a classical picture that helps us to understand how we can divide different materials based on this general division, how we can understand what are metals, what are dielectrics, and what are semiconductors. And I will show you a very classical picture, and hopefully that will help you to understand what's going on in this general division of materials, and what's also going on in terms of semiconductors, and what are their main differences between dielectrics and metals, and on the other hand, what are the similarities. And after that, I will start going through the basic terminology we have on semiconductors. So I will, for example, try to explain to you what are compound semiconductors, what are elemental semiconductors, what are 3-5 semiconductors or 2-6s. And I will end by speaking a little bit about semiconductor doping, what are doped semiconductors, so what are extrinsic semiconductors. And that will provide us a motivational bridge then toward our 2.6 chapter, where we will be first focusing on so-called intrinsic semiconductors. So this is what we will do here on this very first lecture. We will start by going through the main bits of terminology we have regarding semiconductors. And like I already said, what we're trying to do in here, in chapter 6, is that we will extend our previous treatment we had on metals, so also known as conductors. And now we will formulate our treatment to semiconductors. So somehow materials that are not as good as a conductors as metals are, and that's why it's just called accordingly. And in the next chapter, we will be really focusing on the dielectrics. And here I will show you, lo and behold, a classical picture that we can use to divide materials into their different types. So on the far left, I can see that we have metals here, and essentially what makes a material a solid, a metal, is the fact that we happen to have a energy band where we have Fermi level in between the band. So then we have possibility that a tiny amount of thermal energy already can lift up an electron state into a higher state, and then the electrons can start conducting electricity. Then we have this little bit mystical type of a metal known as semi-metals, and there I don't go into the details. If I remember correctly, in chapter 7, we will provide you a little bit of a mathematical tools that you could understand what are semimetals. So essentially, we will introduce to you the so-called tight binding approximation or approach. And using that, we could understand, for example, a little bit better what are semimetals. And then in the middle, we will have these semiconductors. And I'm already spoiling you a little bit so that I'm showing intrinsic semiconductor. So essentially, we will have some kind of band gap between the valence band and the conduction band. And then the Fermi level will be in between. And then in the intrinsic semiconductor case, like we have a little bit of electrons at the conduction band, so that the intrinsic semiconductors can already conduct electricity, but we don't have that many of them since we have the Fermi level in between. And the band gap is fairly large, or at least compared to the case of a metal where we don't have a band gap at all, at least we do have a band gap here when we are speaking of semiconductors. And then when we start doping semiconductors, we can either have a so-called N-type doped semiconductor or a P-type doped semiconductors. Essentially what we are doing here, we will learn this later, is that we are controlling the location of the Fermi level with respect to the highest energy level of a valence band, so this region here, and the lowest energy level of the conduction band. And if we can now adjust the location of the Fermi level, then we can adjust, for example, do we have lots of holes, vacancy states really available in the valence band that can participate in the conduction of electricity, or in the case of N-type doped semiconductors, where we have the Fermi level higher, close to the conduction band, then we start having a kind of fairly good amount of electrons already at the conduction band, and that also then helps out in terms of increasing the electrical conductivity of N-type semiconductor. So this is what we can do with semiconductors. We can adjust their properties, for example, by doping them accordingly. But more on this later, as you perfectly well know, looking at the table of contents for this chapter. And then finally, we have the dielectrics. And essentially in this picture, the difference between semiconductors and dielectrics is essentially it's the width of the energy band gap. So when we are looking at the dielectrics, it's essentially their band gap width that distinguishes them from the semiconductors. So here, this is our focus on this chapter. So we will be focusing on semiconductors, and then later on in chapter 7, we will be treating dielectrics. And as a spoiler alert, please, this is the main thing that can be used to distinguish between the dielectrics and semiconductors. So it's just somewhat arbitrarily, we say that if the band gap energy, Eg, is larger than 3 electron volts, then we call the material a dielectric. And if it's less, then we call it semiconductor. But this is somewhat a murky line. There are a little bit of exceptions, I would call, into this, so that there are, for example, this kind of like a large band gap semiconductors, where I believe, if I remember correctly, the band gap value, the Eg, can be actually larger than 3 electron volts. So this is a little bit a murky line, but in case of rules of thumb, I think this 3 EVs is a pretty good rule of thumb to remember for you, that this is the main thing we should remember for now. And now that we understand that classical picture, I think it's also found in the Wikipedia in a slightly different coloration and way of drawn, but essentially it's a very often used picture. So please understand what's happening on it. So we will now start going into the kind of main terminology regarding semiconductors. And the main motivation why we are in the first place calling some materials conductors, semiconductors and dielectrics, is that it comes from the difficulty that if you would want to categorize materials using some other properties than their electrical conductivities, we would be, sorry, let me rephrase. If you would want to categorize materials only based on their electrical conductivities, then we would be in trouble. And why we would be in trouble is that the values actually range an insanely large amount. So this is one of the highest variations in parameters that we have in nature, so that the kind of electrical conductivity of different materials ranges almost 32 orders of magnitude. So if we take like a very large bandgap dielectric, and we would estimate, we would measure like what is its electrical conductivity, we would see that it doesn't really conduct electricity essentially at all. And then when we would take a metal, which is a very good conductor, such as copper, we would see that the electrical conductivity is many orders of magnitude higher than what we just discovered with our example dielectric. So the variation in the electrical conductivity is huge. And the strange thing, or not so strange thing, but the kind of peculiar thing about this, that the electrical conductivity also depends highly on the actual temperature. So this also would cause us a little bit of a trouble, how we could separate, categorize materials only based on their measured electrical conductivities. So instead, it's far better to distinguish materials. And now I'm saying that we're distinguishing between these three main types. So between metals, semiconductors, and dielectrics. And this distinction can be made far easier by just taking use of the bandgap values. So bandgap values range from 0 to around 11 electron volts. So 0, of course, for the case of metals, and electron EVs, I think this is for the case of magnesium fluoride. So that this is roughly the range of energy bandgap values that we can have in materials. And this is something that we can even remember. So that the value between 0 and 11, it's at least a number I can remember. But if I would need to remember like values that would range from 0 to quite huge values, like what would be 10 to the power of 33, big numbers. So I would be at least lost in trying to remember such large quantities. And like I already said, how do we distinguish between dielectrics and semiconductors? Is that we somewhat arbitrarily call semiconductors more or less all the materials that have a bandgap value less than 3 electron volts. And then all the materials that have a bandgap energy value that is larger than 3 electron volts, then we call them as dielectrics. So as long as we have the EG value smaller than 3 electron volts, then what that means physically is quite a bit of the states that we have, the electron states, are at any specific given of time thermally excited, and they are thermally excited into the conduction band, and there they can readily participate in the conduction of electrons, so conductivity of the material. And then this is what already happens at the room temperature. And here, of course, we mean the room temperature on Earth. So this is in a way, this distinction between dielectrics and semiconductors, it boils down to the circumstances we have on Earth. But if we would be having these same materials in a different planet, where we would have a totally different temperature and different pressure, so we would be in different circumstances, it might be better to have a different value than 3 EVs for the case of dividing between dielectrics and semiconductors. But on the other hand, this is also this division of materials into the 3 different categories. It's somewhat arbitrary. So like this is human invention, and this is not the kind of fundamental property found in natural materials. So that it's rather our way, engineers' way of distinguishing different materials from each other. So please remember EG, 3 electron volts, and also the fact that where it arises from. So on this stage, when we have a bandgap value smaller than this, then at room temperature, considerable amount of electrons are already thermally excited, or considerable amount of whole vacancy states are residing in the valence band, so that the conductivity of the material starts to be non-negligible. Very small. I do not try to say they speak the N-word, like George Bush the Jr. failed back in the days of pronunciating that difficult word, so I will just say that they're very, very small. So I don't say the N word anymore, or at least I try to not say it. Negligible. Ouch, that's so hard. Okay, sorry about that. So now we start uncovering the basic terminology, what kind of semiconductors there are. So we could, for example, form a semiconductor out of a single element. And if we would do so, then we would speak of elemental semiconductors. And essentially, this means that we will have an element that comes from the group 4, so group 14 of the elementary table. So, and this is also known as the carbon group, if you are interested in this kind of slang. And of course, in the new way of categorizing the elementary table, that group will be called group 14 and is called. Examples that we have in here, of course, are silicon, maybe you already remember, and germanium, that are a classical semiconductors that people are using to make devices. And please remember also that we do have in the carbon group also carbon, so we also have the diamond in there as a classical example of a dielectric material that where we have the band gap value of quite large. And in case we don't have a semiconductor formed out of just a single element, but rather we use many elements, then we call the semiconductor a compound semiconductor. And please note that we don't actually have that many elemental semiconductors out there. So essentially, mainly just the silicon and germanium are such. But other examples are quite sparse, because we don't really form solids just using a single element, and that would also already provide a band gap and form a semiconducting structure. So this is associated essentially and boils down all the way down to the kind of number of valence electrons and what kind of microscopic bonds they would really like to form between their adjacent atoms. And then in the case of silicon and germanium, we know that they form into a diamond lattice, and that explains why we actually have the band gap. But more on that in the previous chapters, especially in chapter 2, where we were, and chapter 1, where we focused on the crystalline structures. But okay, in any case, like the most of semiconductors, they are compound semiconductors. And in many cases, they can be electronic with the silicon or germanium. So that means that they together they would form a group 4 semiconductor. So what I mean here is that we can also take silicon and we can combine that with germanium, and we will form a compound semiconductor. It's not an elemental semiconductor since we have 2 elements, but it is a group 4 semiconductor because both silicon and germanium are coming from the carbon group. And notable examples of here would be silicon carbide. Well, I guess some people would also say that silicon carbide is a dielectric, but I guess this is one of those examples that is slightly a matter of taste. Do you call it a dielectric or semiconductor? But at least this is a good example in terms of group 4 compound semiconductor, silicon germanium, also known as CG. So this is a classical family of group 4 semiconductors. And then changing the fraction of how many silicon atoms we have with respect to germanium, then we can actually adjust the properties of the semiconductor quite nicely. Mainly, we can adjust the energy band gap EG value when we would be changing the fraction of silicon with respect to germanium. But more on that a little bit later. And then we can also make a compound semiconductor that is being formed by taking a single trivalent element. So that would be one element coming from the group 3 or group 13. And then we would mesh that together with a pentavalent element. So one element from a group 5 and also known as the group 15 from the elementary table. And these kind of semiconductors that we would form, they would be called 3-5 semiconductors, or just shortly 3-5s. And you can now probably easily understand the terminology here, why they are called 3-5s. So we take one from group 3, and one element from the group 5, and then accordingly we will form a 3,5 semiconductor. And the kind of motivation here is that we can actually form a solid by taking a 1 trivalent and 1 pentavalent element, so that these kind of solids are really being formed. And one of the kind of main but a compound to remember here would be gallium arsenide. So gallium arsenide and indium phosphide in terms of going to the longer wavelengths, in terms of variational wavelengths of the devices. But gallium arsenide gas is really one of the kind of first 3,5 semiconductors that most of the people think when somebody's asking to think of a 3,5. Another possibility of forming a compound semiconductor would then be 2,6 semiconductors, and as you probably already understand how these would be formed, is that we would take one element from group 2 and another one from group 6. Or in principle, of course, in some cases we could have ternary compounds, so where we would have 3 elements. So of course we could in principle have like 2 elements from group 2 or 6s, or 1 element from 6 if such would be the case. But in any case, the terminology is clear, like elements from 2 and 6 groups, and that's how we form a 2,6 semiconductor. Notable examples would be cadmium telluride, so CdTe, and cadmium sulfide. And if I recall correctly, cadmium telluride is, at least it used to be, the most used semiconductor when you are making a photovoltaic cell. So if you're making a solar panel, it used to be the case that cadmium telluride was the most used semiconducting material to make them, if I remember it correctly. I might be wrong, but it might be this. And usually these 2,6 semiconductors, they exhibit larger bandgap values, so the EG value is usually larger. And this is, of course, a very big difference between 3,5s and 2,6s. And I would not spoil you the fun for you to think what this may possibly imply in terms of the applications where we could use them. But I really recommend you to think that what possible good we could have by having a semiconductor which would have a larger bandgap. And what would be the kind of main difference, or at least differences, between a larger bandgap value semiconductor and a smaller bandgap value semiconductor. I think this is a very good Gedanken experiment for you to kind of figure out how things change when we are going into different types of materials. And then, like we're almost done for this lecture, I will speak a little bit about binary semiconductors first, and then go into doping. So pure binary semiconductors, like we can really change their properties. So meaning that we can engineer them by, for example, we can change the bandgap values EGs by forming ternary compounds. So what's a ternary compound? That we just add a third material into the mix. So a prime example of such a mixture, a ternary semiconducting compound, would be aluminum gallium arsenide and in short, AlGas structures. And here the reasoning is that when we start putting aluminum into the mix of gallium arsenide by just adding a third material, we can change essentially the bandgap value. And if you can change the bandgap value, we are changing a lot on the properties of the semiconductor. And then, for example, when we would be thinking of applications where the bandgap value actually matters quite a bit, then this would be the way how we could change the kind of operation wavelengths and regimes of our semiconductor devices. And in addition to this kind of ternary compounds, there's also CG. It's not a ternary compound, it's a binary compound. But by changing the fraction of silicon with respect to germanium, so in CG alloy, we can also change the bandgap values. And with that, like a lot of things can be actually tweaked in terms of the properties of the materials. So when we are changing the fraction of aluminum, we are using a notation of aluminum X, gallium 1 minus X, and arsenic. And we don't change the fraction of arsenic in the material. And here X ranges from 0 to 1. And this is, of course, the kind of term that gives us the actual chemical composition of our ternary compound. So depending on how much of aluminum we have, then we change the amount of gallium respectively, and then we will have a slightly different materials. And please take a note on here that when we are adding a third element into the mix, we cannot add arbitrarily different elements here, but their lattice constants and of course the lattice structures should be same. So the crystalline structure should be the same and the lattice constants should be roughly the same for that we could actually make a solid and grow it and then have a stable solid compound. So this is the kind of main limitation that restricts what kind of ternary compounds and what kind of binary compounds we can make. So that the crystalline structure should also be quite similar, and that restricts things quite a bit. But more on that, especially on our course on semiconductor physics, when we are really covering more on these kind of subtleties, that how can we adjust the properties by changing the composition of the material. And then the kind of main thing that we will be focusing here on this course and on our chapter 6 is that we can also change the properties of semiconductors by adding impurities into the semiconducting mix. So essentially we can adjust the properties by doping semiconductors. And this gives us the kind of final bit on terminology. So when we have an undoped, non-doped semiconductor, a so-called pure semiconductor, then we could also call that kind of semiconductor an intrinsic semiconductor. So we don't have any impurities added intentionally into the semiconductor, and that's why we call it intrinsic. Of course, in real life, there's no such thing as ultra pure semiconductor. There will always be some impurities on it. So that like when we call something intrinsic, it just means that we have not intentionally added impurities into the semiconductor. But of course, there will always be some impurities, so that we cannot really avoid that when we are making materials. And then the second type of a semiconductor that we can have is that then we will have this impure one, and then these are also called doped semiconductors or extrinsic semiconductors. And these are the types of semiconductors that we have intentionally doped. So we have added impurities into the mix, and that will change the properties of the semiconductor quite a bit, especially the electronic properties, as we will soon learn in the upcoming lectures. But here, please note, the amount of doping that we use, it's not very much. So we only add a few parts per million, few parts per billion amount of doping. So it's not really that we would be forming a kind of considerable fraction of a third element into the mix. So L-gas is not a doped semiconductor as such, because the amount of doping is totally different. So when we are forming a ternary compound, then we are actually doing something different than doping the semiconductor. And when you do ternary compounds and change the chemical composition, we are really mostly interested in changing the energy band gap values, so adjusting the band structure. And when we are adding doping, what we are doing is that we are really changing the amount of population of electrons that we have in the conduction band, or the population of vacancy states, so holes in the valence band. So this is what we are doing, but we are not changing, we are not yet modifying the band structure of our semiconductor by doing doping into the material. So I will thank you now, we are done with the very first lecture. I hope this was a good starting point, and next we will be focusing on these intrinsic semiconductors first, so that we would appreciate and understand what are their electronic properties. And once we have fully nailed intrinsic semiconductors, then we will go into extrinsic semiconductors. So thanks for listening, and please join me in the next lectures. Thanks and bye-bye.